Hello friends, welcome to my channel Eccentric Learning. I hope you have gone through the first part of the remainders where I have covered the basics of remainder, what is a negative remainder, how we can find the remainder of the higher powers of a number divided by a divisor, and so on. So if you haven't gone through that video till now, the link has been given in the description box. Please go through it. Also, if you like my videos, then do subscribe my channel and also share with your friends. In today's video, we are going to see some theorems like binomial theorem, Permissible theorem, etc., which will help us to find the remainders easily in certain cases. So let us start with today's video. Before saying how we can find the remainders using binomial theorem, first let us see what is a binomial theorem or a binomial expansion. Suppose if I have a binomial a plus b, and this has been raised to some power n, where n is some natural number, then the binomial theorem or the binomial expansion of this binomial is given by nc0 a raised to power n plus nc1 a raised to power n minus 1 into b raised to power 1 plus nc2 a raised to power n minus 2 into b square plus and so on till ncn minus 1 a b raised to power n minus 1 plus ncn b raised to power n, where n belongs to natural number n and ncr is the number of ways of choosing r objects out of n distinct objects and is given by n factorial upon r factorial times of n minus r factorial, where n factorial is given by n into n minus 1, n minus 2 till 3, 2, 1. For example, if I have 5 factorial, this can be written as 5 into 4 into 3 into 2 into 1, which is 120. We shall be discussing in more details about NCR in the permutation combination chapter. For the time being, simply remember the definition of NCR, which is simply the number of ways of choosing R objects out of n distinct objects, and the mathematical formula of NCR is given by n factorial upon r factorial times of n minus r factorial. Now, let us see some facts that would be worth observing in the expansion of a plus b raised to power n. So the first term is nc0 a raised to power n. The second term is nc1 a raised to power n minus 1 b raised to power 1 and so on. And the last term is ncn times of b raised to power n. So altogether, the number of terms in this expansion would be n plus 1. And the sum of powers of a and b in any term would be n. For example, in the first term, we have the power of a to be n and the power of b to be 0. So the sum of powers of a and b would be n. Similarly, in the second term, the power of a is n minus 1 and the power of b is 1. So again, the sum would be n and so on. Also, there is a property of combination, which is NCR is equal to NC n minus R. So if R is equal to 0, that is the first term. In that case, NC0 would be equal to NCN. And if R equal to 1, that is the second term. In that case, NC1 would be equal to NC n minus 1 and so on. So from this, we can see that the coefficient of the first term would be same as the coefficient of the last term, and the coefficient of the second term would be same as the coefficient of the second last term and so on. So if we expand a plus b raised to power 10, in that case, this can be written as 10c0 a raised to power 10 plus 10c1 a raised to power 9 times of b plus 10c10 a raised to power 0, which is 1 b raised to power 10. So from this expansion, we can see that the number of terms in this expansion would be 10 plus 1, that is 11, and the coefficient of the first term, that is 10c0, is same as the coefficient of the last term, that is 10c10, and the coefficient of the second term, that is 10c1, would be the same as the coefficient of the second last term, which is 10c9 and so on. and the sum of powers of A and B in any term is 10. So any binomial raised to some natural power can be expanded simply by using the binomial theorem. Now, let us see one example to see how we can use the binomial theorem to find the remainders. Suppose if I have this number 19 raised to power 23 and this number is being divided by 36 and we want to find the remainder. Well, if we look closely here, 19 can be written as 18 plus 1 and there is a power 23 divided by 36. Now, when we expand this 18 plus 1 raised to power 23 using binomial theorem, there will be many terms which would be containing a multiple of 18 and 2, that is a multiple of 36. So all those terms won't be giving any remainder when divided by 36. So we'll be focusing on only those terms which may not contain a multiple of 18 and 2. So let us try to see what are those terms. So if we expand this would be 23 C0 18 raised to power 23 plus 23 C1 18 raised to power 22 into 1 raised to power 1 plus and so on plus 23 C23 1 raised to power 23, and this is divided by 36. Now if we look closely, we know 36 is 2 times of 18 and all the terms except the last term and the second last term would be containing a multiple of 36. Why? Because 18 raised to power 23 would be 18 times of 18 times of 18 till 23 times, and this would be containing a multiple of 18 and 2. So the first term would be containing a multiple of 36. In a similar way, the second term, the third term and so on would be containing a multiple of 36. So all the terms except the last term and the second last term would be containing a multiple of 36. So whatever the remainder we'd be getting from the last term and the second last term when it is divided by 36. Now 23C22 into 18 into 1 would be same as 23C1 times of 18, because NCR would be equal to NCN minus R, and 23C1 if we calculate, this would be 23 times of 18. So this would be 414, and 23C23 times of 1 raised to power 23 would be same as 1 because NCN is 1. So the remainder of 19 raised to power 23 upon 36 would be same as the remainder of 414 plus 1 divided by 36. So this would be same as the remainder of 415 divided by 36, which would be giving us the remainder as 90. You may have found it a little bit difficult to find the remainder using the binomial theorem. But if you look here carefully, we just have to deal with the last two terms of this expansion, which has to be divided by the divisor to find the remainder. So with practice, it will be very easy to find the remainder using the binomial theorem. Well, in this case, we can also find the remainder in a different way. I know 19 square is 361 and 19 raised to power 23 can be written as 19 times of 19 square to the power 11, and this would be 19 into 361 raised to power 11. So the remainder when 19 raised to power 23 is divided by 36 would be same as the remainder of 19 divided by 36 times of remainder 361 to the power 11 divided by 36. So the remainder of 19 by 36 would be 19, and 361 divided by 36 will give us a remainder of 1, and 1 raised to power 11 would be 1. So this would be 1. So the final remainder would be 19 times of 1, that is 19, which is same when we have used the binomial theorem. So either we can use the binomial theorem or an alternative way to find the remainders. Now, let us try to find out the remainder when 17 raised to power 17 is divided by 64 using binomial theorem. I know 17 can be written as 16 plus 1, and we know that 16 times of 4 gives us 64. So, if we use the binomial theorem in 16 plus 1 raised to power 17, in that case, this can be written as 17C0 16 raised to power 17 plus 17C1 16 raised to power 16 times of 1 plus 17C2 16 raised to power 15 times of 1 square plus and so on till 17C16 times of 16 into 1 raised to power 16 plus 17C17 times of 1 raised to power 17. Now 64 is 16 times of 4. So except for the last term and the second last term, all the other terms will have a multiple of 16 and 4. So the remainder when 17 raised to power 17 is divided by 64 would be same as when the last two terms are divided by 64. So the second last term 17C16 into 16 would be same as 17C1, which would be 17 times of 16, and that would be 272. And the last term, that is 17C17 times of 1 raised to power 17 would be 1. So the remainder of 17 raised to power 17 divided by 64 would be same as the remainder when 272 plus 1 is divided by 64, which is same as the remainder when 273 is divided by 64, which is 70. Now, let us see when 49 raised to power 60 is divided by 100, then what would be the remainder? Well, when a number is divided by 100, then the remainder is same as the last two digits of the number. So again, simply by using the binomial expansion, we can write 49 raised to power 60 as 50 minus 1 raised to power 60, which can be written as 60C0 50 raised to power 60 minus 1 raised to power 0 plus 60C1 50 raised to power 59 minus 1 raised to power 1 and so on. Now, all the terms except the last term will contain a multiple of 100. Why? Because in the first term, we have 50 raised to power 60. So it will be containing at least 2 zeros. Similarly, in the second term, we have 50 raised to power 59. And this would be again containing at least 2 zeros and so on. And in the second last term, we have 60C59 times of 50 into minus 1. And 60C59 is same as 60C1, which would be 60. And 60 times of 50 will give us 3000, which will again contain 2 zeros. So all the term in this expansion, except the last term, will have 2 zeros. So when 49 raised to power 60 is divided by 100, in that case, the remainder would be same as when the last term of this expansion would be divided by 100. Now we know 60C60 would be 60C0, that is 1, and minus 1 raised to power 60 is also 1. And all the terms of this expansion except the last term will have the last two digits as 0, 0, and the last term will have the last two digits as 0, 1. So the remainder when 49 raised to power 60 is divided by 100 would be same as 0, 1. So you can see how simply by using the binomial theorem, we can find the remainders. Now let us see what is Fermat's little theorem. Suppose if I have a number which is of the form of a raised to power p minus 1, and this number is divided by the number p, where p is a prime number and the HCF of a and p is 1, that is, the number a and p are co-prime. In that case, the remainder of a raised to power p minus 1 upon p will always be 1. For example, if I take this number, say 6 raised to power 4, and this number is divided by say 5, and I want to find what is the remainder. I know 6 raised to power 4 is 6 square into 6 square, that is 36 into 36, which is 1296. So the remainder of 6 raised to power 4 upon 5 would be same as the remainder of 1296 divided by 5. And when 1296 is divided by 5, in that case, the remainder is 1. Now, we can also use Fermat's little theorem in this case. Why? Because the remainder of 6 raised to power 4 upon 5 can be written as the remainder of 6 raised to power 5 minus 1 upon 5. And this number is of this form. And the remainder of a raised to power p minus 1 upon p is 1. So the remainder of 6 raised to power 5 minus 1 upon 5 would be 1. So whenever we want to find the remainder of a number divided by a prime number, and the number is of this form or can be transformed to this form, then the remainder will be always 1. Now, let us see these two questions where we can find the remainder simply by using the Fermat's little theorem. So let us start with the first one. Here, we need to find the remainder when 7 raised to power 241 is divided by 61. Here, 61 is a prime number, so we can think of using the Fermat's little theorem. Now, 7 raised to power 241 can be written as 7 times of 7 raised to power 4 to the power 60. Why? Because 7 raised to power 4 to the power 60 would be 7 raised to power 240 times of 7 would be 7 raised to power 241. Now, we need to find the remainder when this number is divided by 61. That is when 7 into 7 raised to power 4 to the power 60 is divided by 61. So the remainder of this can be written as remainder of 7 upon 61 times of remainder of 7 raised to power 4 to the power 61 minus 1 upon 61. Now this is of the form of a raised to power p minus 1 upon p. So this part will give us the remainder as 1 by Fermat's little theorem, and the remainder when 7 is divided by 61 is 7. So the remainder would be 7 times of 1, that is 7. Now let us see the remainder when 26 raised to power 74 is divided by 37. Well, here again we can see that 37 is a prime number. So let us try to write the number in the form of a raised to power p minus 1. That is a raised to power 37 minus 1. So 26 raised to power 74 can be written as 26 square times of 26 square to the power 36. Now the remainder of this when divided by 37 would be same as the remainder of this when divided by 37. So this can be written as remainder of 26 square divided by 37 times of remainder of 26 square to the power 37 minus 1 upon 37. Now again, using Fermat's little theorem, this part will give us the remainder 1, as this is of the form of a raised to power p minus 1 upon p. So now the remainder would be simply the remainder of 26 square upon 37 times of 1, which would be remainder of 26 by 37 times of remainder of 26 by 37. Now this will give us a negative remainder of minus 11, and this will also give us a negative remainder of minus 11, and this would be divided by 37. So the remainder of 26 raised to power 74 upon 37 would be same as the remainder of 121 upon 37, which would be 10. Well, from here also directly we can write the remainder of 26 square upon 37. Why? Because 26 square is 676. So this would be same as the remainder of 676 upon 37, which would be 10. So you can see how easily we can find the remainders by using the Fermat's little theorem. Now let us see what is Wilson's theorem. Suppose if p is a prime number, then p minus 1 factorial plus 1 would be a multiple of p or would be completely divisible by p. So what does this mean? Okay, so let us take an example here. Let us assume a prime number p to be 5. So p minus 1 factorial would be 5 minus 1 factorial, which would be 4 factorial. That is 4 times of 3 times of 2 times of 1, which is 24. So p minus 1 factorial plus 1, that is 24 plus 1 would be 25, which is completely divisible by 5. So if p minus 1 factorial plus 1 is completely divisible by p, in that case, the remainder when p minus 1 factorial is divided by p would be minus 1. That is, the actual remainder or the positive remainder would be simply p minus 1. In this case also, that is, when p was 5, then p minus 1 factorial, that is 4 factorial, which is 24, would give us a remainder of 4, that is 5 minus 1 when divided by 5. Now, if I want to find the remainder when 60 factorial is divided by 61, in that case, by using Wilson's theorem, we can say that 60 factorial divided by 61 will give us a negative remainder of minus 1. So the positive remainder or the actual remainder would be simply minus 1 plus 61, which is 60. So whenever we want to find the remainder when p minus 1 factorial is divided by p, where p is a prime number, then simply by using the Wilson's theorem, we can say that the remainder would be p minus 1. So that's it for today's video, in which we have seen some theorems like binomial theorem, Fermat's theorem, and Wilson's theorem, and how we can find the remainders using these theorems. I would also suggest you all to practice more questions on remainders using these theorems and the other approaches that we have discussed in this and the last video, because the more you practice, the more you learn. So I hope you have learned something in today's video, but if you have any confusion, you can watch the videos again, and still if you have any doubts, you can put it in the comment box. I will try to answer each one of your queries. So if you like my videos, then do subscribe my channel and also share with your friends. I'll see you all in my next video. Till then, keep learning, keep sharing, and keep growing. Thank you.